Out of 500 machines making the same product, 5 items are selected at random from the output of each machine and inspected. The results of this inspection are given in the table shown on the screen. Is the binomial distribution a good fit for this data? Okay, now that we have our data here set up, we need to work out the mean. So to work out the mean, we're going to multiply the number of faulty products by the frequency. So we get 0 times 19 gives 0, 1 times 109 gives 109, 2 times 179 gives 358, and so on. Which gives a total of 1,100. So therefore, the mean is equal to 1,100 divided by 500, which is equal to 2.2. Now, these were taken from groups of 5, so therefore the probability that one is actually faulty is 2.2 divided by 5, which equals 0.44. So the next thing we need to know, since we're trying to work out if these numbers fit a binomial probability distribution, is what would a binomial probability distribution look like in this case if it had n equals 5, p equals 0.44. So you know the formula. We're filling this in with the binomial probability. And you know the formula, it's going to be 5, choose the number of products, times this to the power of this, times 1 minus this, times to the power of 5 minus this, right? So, therefore, calculating this, we get 0.05507. Now, of course, all of these should add up to 1. If you had a probability distribution which kept going on to infinity, we would simply make the last cell equal 1 minus the sum of the rest, so that they all add up to 1. So now, what we're saying is, if it really was binomial, this would be the probability, so we can calculate the expected frequency. Now, since there are a total of 500 items, we're expecting this to add up to 500 items as well. So we're going to multiply 500 by the individual probabilities to give us the expected frequency. Okay, so we notice these, just like these, start off small, get bigger, and then get smaller again. Is that enough? Well, to answer this, we calculate our statistic, which is basically our expected value minus our observed value, that would be this one, squared divided by our expected value. So, we get 2.64, 0.01, 0.47, 1.16, 2.97 and 0.19. Now, if this really did come from a binomial distribution, these two columns would be virtually the same, and therefore this will be really close to 0. So we're going to add the total up to find out how much we've got, which is 7.44. Now we need to compare that with the value in the table. Okay, so we need to compare this number, our statistic that we've calculated, with the chi-squared value in the table. First, to work out the chi-squared value in the table, we need to know the number of degrees of freedom. So this is equal to the number of cells we have, which is 1, 2, 3, 4, 5, 6, minus the number of parameters that we used to calculate these values here. Well, to calculate these values here, the first thing we needed was to calculate those binomial numbers, which used the p-value here of 0.44. The second value we used was we multiplied these numbers by the total frequency, which gives us 500. So that was what gave us these numbers. So we've got 1, 2. So 6 minus 2 is equal to 4. So now we look up on the table for chi-squared value. For alpha equals 0.05 with 4 degrees of freedom, we get 9.488. So if we look at our probability distribution, which looks like so, we have at 9.488, this area here is equal to 0.05, and this value here is over here somewhere, 7.44. So this is not particularly extreme, it's quite small. So therefore these are closer to 0 than our cutoff point. So therefore we're going to assume that this pretty much is 0, and therefore we're going to accept it as a binomial distribution.